So last time, what we started doing was that we looked at the fundamental definitions of where the circuit assumptions come from. We saw that generally electrical systems are governed by what? Maxwell equations, right? Maxwell's equations, but Maxwell's equations are quite general, and they're applicable in a broad range of applications. So now we saw that there were special cases where they simplified to much simpler rules that you could apply in a meaningful fashion and in a much more effective fashion. Right? And so what were those? Can somebody refresh everybody's memory on those? Do you remember what they were, those special cases? Yes?
There's the circuit case where like your dimension scale is substantially less than the wavelength.
Right. So when the circuits is when basically, as you pointed out, where the dimensions are substantially smaller than the wavelength. There's the alternative, which is when the wavelengths are much larger than the dimension. I'm sorry, much smaller than the dimensions, which would be the optics case. And then everything in between is called microwave or the general electromagnetic problem. So the case we are interested in this class is really the circuits case, where the dimensions are much smaller than the wavelength. Another way to think about that was that the speed of light is infinity. We saw that. Propagation happens instantaneously. There's no delay. And you can see that's critical, that's important, particularly when you later on, if you look at things that radiate, things that, for example, antennas and things of that sort, they rely on that delayed action. That delayed action is what makes it possible for something to radiate. If you don't have delayed action, it's very difficult to radiate, if you will. But that's a separate discussion. Now, so the other thing that we did, the other part of the conversation that we had was this concept of voltage and current, which we defined. We are not going to redefine. And also we talked about the concept of power. So quickly, just to refresh your memory, the voltage was defined as the rate of work done to the charge. It's normalized to the charge. So the voltage between points A and point B was the work it would take to take a particle from point A to point B and to be able to, normalize by the charge. And the reason you do it with an infinitesimal charge is that you want to induce the least amount of perturbation to the field, right, itself. Because think about it. Let's say, how do you generate the field to begin with? Let's say you have electric field in this room. How do we generate it? Right, you have charges here and there, right? So you may have placed a big charge here, a big charge there, one over there, one over there. So if I bring a gigantic charge here to test this, measure the voltage, this can start attracting and repelling these charges and then displace them and mess the field profile that you're trying to measure, perturb what is being measured, right? So now the other thing that we defined was the current. The current was the rate of flow of charge as a function with time. Obviously it's a rate. So that was also the definition that we had. So we said if you have a cross section and then look at how much charge crosses a certain cross section and look at that rate over time, that's basically what the electric charge is, electric current would be defined as. Of course, this had units of amperes, which would be coulombs per second. This has units of volts, which is again joules per coulomb. Now, the other thing that we notice is that if you look at power, the basic definition of power is defined as the rate of work being done, right? The rate of energy transfer, or the rate at which work gets done, is performed. Now, if and only if that's done through electrical means, it's meaningful to divide and subtract by Q. So again, we are making we made a distinction between what's physics and what's mathematics. And you have to understand this difference and capture them, because they're different things. Mathematically, you can always do this, right? I can mathematically divide and multiply anything by anything, right? By some fixed quantity, as long as it's not zero, right? But for these quantities to have meaning, physical meaning, it only applies to the work that's done electrically through this charge that's being transferred. So it's two things happening in the same place. We have to understand in our head and decouple these things in the way we think about things. So now obviously this, by definition, if it's done electrically, this is the voltage and this is the current. And that's why power is the product of the voltage and the current. And the instantaneous power at any point is the voltage at that instant times the current at that instant. Now, the other thing that we define is, well, okay, if you're looking at power, that's nice and good, but what happens is that you generally may be interested, for example, in terms of the amount of work that's done or the energy that's used over a period of time. And one of the things that we looked at quickly was we said, okay, if you're looking at work done from time 1 to time 2, or the energy is basically the integral from t1 to t2 of p of t dt. Right? And that essentially means that if there's fluctuation in the rate of work, in other words, the power versus time, it fluctuates. The energy that you use on your phone is not constant. Sometimes you're making a phone call, sometimes you're downloading data, sometimes you're watching something, sometimes it's completely off and in a low power state. So the total energy that this spends or uses over a period of time, let's say from T1 to T2, which determines how much of your battery you really use, is determined by the area underneath this thing, which is that integral. And I'm assuming everyone knows integration and summation and, differentiation cold. You need to, I assume everyone, that's a completely well understood concept here. So that was as far as we went last time. So now the other thing that comes in is that there's some definitions. So we'll go through some more definitions today, and then we'll start applying them and using them. But so there's one definition called passivity, as opposed to activity, being active or passive, an element being passive or active. So, and there's something else that we define. Technically, it's one of those, but it's like a special case of one, which is the reactive. Things that are, so we are going to be talking about things that are passive, things that are active, and things that are reactive. Now, when we talk about passive and active, we mean in terms of energy, right? So, in short, before we write the mathematical definition, a passive element is the one that does not provide net energy. It cannot give you more energy than it was ever given. Right? And an active element is one that can. Okay? So how do we define that? How do we come up with a definition? So if we define, think about the definition. How would you go about defining this before we actually define it? We want to define something that captures that concept. So we want to look at the total energy that this element has ever absorbed, right? And by the way, for an element, what we said, when P is greater than 0, it means that it's power delivered to it. And if P is greater than 0, it means that, or absorbed. And this means that it provides power. So if you wanted to look at how much energy it has ever taken, how do we do that? What is the energy it has taken over the entire time up until now of an element? How can we use this to capture that? Yes?
Integrate from some T naught to...
Yes. And if you wanted to capture ever, what is that T naught? Negative infinity, yes. So from negative infinity to t, so let's call this W of t, of P of t dt. Right? That's the total energy it has ever absorbed. And you can say something is passive if for all times, for all t's, W of t is greater than 0. Meaning that there's no time at which it has provided more energy, it had provided more energy than it had ever absorbed. Right? So if it did provide energy, it was something that it absorbed before, but it was not more than what it absorbed. So it can still capture energy, and it can provide instantaneous power. But the sum of all the power that it has, energy that it has provided from negative infinity to now, can never exceed. It can't be positive. I mean, the work is positive, meaning that it has always absorbed energy. When it's positive, it means that it's absorbing. So now, and by definition, of course, something is active if there exists a single time at least where this is negative. So I can write it mathematically as like there exists a time, etc., right? So now if this were to come from a two-terminal element, and we talked about this briefly, the two terminal elements, we have a current I and a voltage V. Now, you got to be careful about this. Of course, if you're in circuit domain, we know that these two currents have to be always equal. Because why? Sure, yes, exactly. Or propagation is instantaneous, speed of light is infinity, there's no charge storage in there, as you said. So there are different ways to think about it, but now, the other thing to keep in mind is that, let's say this is terminal A, this is terminal B, you could write this VAB. The fact that this is shown as positive and negative, and this current is flowing in this direction, doesn't mean that the actual current is flowing in that particular direction all the time, or at any given point in time, or the voltage is actually in this orientation. This is just a convention for defining this voltage and current. And the way we do it is that we keep a convention, and if it's flowing in the other direction, I becomes negative. It's an algebraic function. If the voltage is the other way around, V is negative. This is actually a lot more easier to deal with than trying to keep track of it every time. Say, okay, is this positive, negative? Because first of all, things change. You can't come, I mean, as we go, and right now in the first couple of lectures, things will not be changing very much, but then you will see that we will be dealing with changing things. Actually, most of this class is dealing with things that have dynamics. And, you know, it's a nightmare if you wanted to keep track of the actual, is it going this way, now it's going this way, this way? No, it's always going this way. Sometimes it's positive, sometimes it's negative, right? And it's always pointing this way. This is the polarity of the voltage. Sometimes it's negative, sometimes it's positive. Maybe it's all negative all the time. Doesn't matter. So this is the convention we are going to be using. This is the convention that's a little bit more professional and practical and scalable to larger problems than trying to, you know, it may be easy to do it if you have like 2 resistors, or maybe 3 if you are really good at tracking things. But if I give you something with 50 resistors, you can't do that. And if I give you things that change with time and every one of them changes in a different way, which we will deal with, there's no way. So we are developing tools that allow you to handle these things and allow you to develop tools that can handle these things, namely computer programs and things of that sort that can handle these things. You won't write, I mean, hopefully you won't have to solve a problem with 100 elements by hand. Although there may be benefits to doing that at some level, but that's beside the point. Anyway, so going back to the discussion, what I was trying to say that if you have a two-terminal element, you can actually look at this V and I, right? You can say V versus I or I versus V. So if you're here, we are doing I versus V. Now, if something is passive, right, what does it mean about this current and voltage? It means, and if it was just like this, and this is a special case, by the way, that I'm showing. This is not a very, very as general a case as it can be. But if you have something that's passive, it means that this current and this voltage need to be having these polarities or be of the same polarity, because the product has to be positive, right? If you want P to be positive, the product has to be positive. So we're out of these 4 quadrants. So let's call this first, second, third, and fourth quadrants. Which one of these quadrants satisfy the condition of them, the product being positive? First and third, right? So as long as you have some element that has a characteristic that goes through first and third and doesn't go into the second and fourth, then you are good. That's a passive element. This is not all passive elements. This is a special case of passive element. This is essentially, let's put it, if you want to think mathematically, this is a sufficient condition. If you have something like this, it's going to be passive. But not all passive things definitely can be even defined this way. As we will see, for example, a capacitor cannot be defined as a V to I characteristic. We'll see that a capacitor is defined as a QV relationship, not an IV characteristic. And that's basically the fundamental definition of a capacitor. So here, essentially, these are the kinds of things that we generally call resistors, whose current is a function of its voltage, or its voltage is a function of its current. There are things whose charge is a function of their voltages. and those are called capacitor. There are things where the magnetic flux is a function of their current. They're called inductors in general. They can be nonlinear, they can be time varying. We'll talk about those as we go forward. But this is the thing. But this is a passive component. So if you have an IV characteristic that is in the first and third quadrant, it would be passive. And from the hydraulics analogies, you can think about it like you can have reservoirs and you can get water from one to the other. If you can get water from the lower reservoir to the higher reservoir, it means that there's a system that can actually take energy, inject energy, right? If you have a pump that takes water from the lower reservoir and puts it up in the higher reservoir, then you have an active system. So you can have this and that, and you can have a little tube here going into a little pump here, and having water going in this direction. Or it could be even hooked up here. Right? So you can have water flow in this direction. So that's like an active system. Now, so give me an example of an active. Let me show you something. Let me give you an example and you tell me what it is. On the same IV characteristic. This is something that has this IV characteristic. This is its IV characteristic. It's some constant horizontal line. Right? What is that IV characteristic? What is that? It's a battery. It's a source. It's a fixed voltage source, right? It's something whose voltage is independent of its current. It provides a fixed voltage. Let's say, I don't know, 1 volt. Let's make it more interesting. 1.5 volt. Right? At all time, no matter what the current is. Now, this is a little bit more than a battery, or a little bit less than a battery, I guess, depending on how you think about it. It's an ideal battery. It's the perfect battery. This doesn't exist. This really does not exist. And I can show you something that will tell you probably that it cannot exist in a few minutes. But this is interesting, right? I mean, but this is a pretty interesting view of the thing. But this is, and what is it, passive or active? It's obviously active because it goes into the second quadrant. It can provide energy. Now, how about a capacitor? I mean, we haven't really formally defined a capacitor. We will define capacitor formally, and we deal with it formally. But you've probably, I'm sure everyone has seen a capacitor here and understands what a capacitor is, right? So a capacitor, is it active or passive? Well, no, it can't be both, right? I mean, because we define active and passive, right, as logically exclusive. We define active as the opposite of passive. So active, by definition, is passive bar. Because of the way we define it, it can't be both. I mean, you could define it in a different way. But it's actually, but you have an interesting observation, you've made an interesting observation, which is that it falls into somewhere like an interesting gray area-ish, at least apparently. But it has to fall, with this definition, it can't be in both camps, right? So think about the definition. When in doubt, go back to the definitions. Yes? It's passive. Why? It's not generating any more energy, as you said, and it's basically it's whatever you charge it to, right? So it can't give you more than what you have put into it. Right? Does it make sense? Make sense? So that's based on the integration. Yes? When it's charging, it's absorbing energy, right? So at that point, this is positive. Even this is positive. Let's go. Actually, that's a good question. Let's go over that cycle. So the question is, how about when it's charging? And the way to think about it is, well, let me do it here. So let's say this is the charging cycle of your capacitor, right? So this is time, and this is P. And remember, with the convention that we defined, when it's positive, it is power going in. It's absorbing power. When it's negative, it's providing power, sourcing power. So let's say it's discharged at time equal t equals 0, right? Before that, and let's say there's no prior charge on this. So when you start charging it, which way is it? Is it positive or negative? When you start charging it. Exactly, positive, right? Because you start charging, and usually things don't charge that way, they charge this way. But that's a different thing because of the chemistry of the battery and all sorts of interesting things. But so you are delivering power, right? And then at some point you stop charging, and then you stop using. So depending on how you're using, you're watching a movie here, you're talking to your friend, you're going to sleep, etc., etc. Well, it's a capacitor, so it's okay. You can have a big capacitor, charge it that way, right? You're using it in some different ways. Now, can this integral, can the area under this thing, at any point in time, which is basically what we are interested in, right? Well, in this case, from 0, but can this area at any point become negative? No, because you can't take more out of it than you've put in. Does it make sense? Any more questions? Feel free to ask questions. Yes?
For like a rechargeable battery, would you consider that an active one? Because, I mean, like, you know, for circuit analysis, it seems like you want to make the distinction active versus passive for like anything else.
That's a very good, that's an excellent observation. So you're asking the question is that how about a rechargeable battery, because you're putting energy into it and you're taking the same energy out and probably not even as much as you put into it. That's absolutely right. Even if you think about, so it depends on what, so this is really a good question. And these definitions and the results, as you will see, change depending on where you draw the line around your system, how you define your system. If you say, okay, my battery, the chemistry of my battery is outside the box I'm interested in. So this is chemistry. I don't like chemi stuff, so I don't want to worry about it. I'm an electrical guy. I only think about the EE stuff. So in my world, this is an active thing because it's coming from the chemistry. But you could argue that at some point, some energy went into the system, right? At some point, past Big Bang, something happened, and that caused the certain chemistries to form, and some energy came from something else. And if you integrate all of those things, if you truly do it from negative to infinity on all sources of energy and power, there is no such a thing as an active, right? I mean, everything is passive except for Big Bang, right? That there was one instant of activity, and everything else is passivity beyond that, which may not be too far from the truth. But anyway. So here's the thing, right? But if you think about it that way, it depends on where you draw the line. That's an excellent question. So a lot of, and this is a recurring theme. You will see that depending on where you draw the line and how you define your system, you can get to different conclusions. So you need to be clear about where you draw these lines and your system line boundary is. Great question. Any other questions? Yes?
You were talking about like the voltage and current flip-flopping between negative and positive. But could you have like a resistor, for example, be active if you made the current go the opposite way somehow?
So sure. So the question is that if currents flip-flop, what happens? But if for a resistor, for the current to flow in the opposite direction, what has to happen to the voltage?
It has to flip.
Also has to flip. So the product remains positive. Right? That's what it means to say it's in first and third quadrant. So you have both negative or both positive. So, and that's exactly the definition of a resistor. It's a mathematical definition of a resistor. Now, as I said, I mean, there's a physical resistor, which has all sorts of complexities, and we'll talk about that a little bit in a few minutes. And there's a mathematical resistor, which is technically this relationship, which is I equals F of V. Or V equals F of I. And this is an abstraction of that physical resistor. Now, it's only as good in predicting as accurate an abstraction that is. If you don't model certain things, you won't see their effects. Now, actually, that goes back to this question of the source, that source that we talked about earlier, right? The voltage source. If you think about this voltage source, this is really a mathematical abstraction, right? This is like saying V equals V naught, right? So, and as such, it can't exist in reality. Not exactly. And you will see as such, it will result in some apparent contradictions. And we'll talk about that in a second. But going back to the capacitors, right? So capacitors technically are what? So what conclusion do we arrive at? Passive or active? Passive, right? So they're passive. However, they're a special kind of passive. They are passive that at some point can provide energy to you. A resistor cannot. For a resistor, actually, not only this is true, but this is also true. Right? Because of this IV characteristic. In a resistor, even the instantaneous power cannot be negative. Even there's not one instance where it can actually provide power. Okay? Yes?
Greater than 0?
I'm sorry. Yes. Thank you. Correct. Thank you. Yeah, greater than 0. So, right? But this is not true about a capacitor. You saw the example, right? We drew a picture here. So in a capacitor, if this is P of t, here is positive, this is negative. But still, the integral is what? Greater than 0. It always absorbs net power. But so you could actually define reactive as this. Reactive is a subset of passive. However, it has an extra condition. What is that extra condition? There exist times where P of t is negative. While for all time, I'm writing using mathematical notation. I'm actually being a little bit pretentious here, to be honest with you. But I want to emphasize that these are mathematical abstractions, in addition to being a little bit pretentious. But the primary purpose is to really show you that these are mathematical abstractions. That's why I use mathematical language to write them, not to be confused with physical realities. Okay? Any questions? No? All right. So let's continue our discussion. Let's see, where's the best place? Let's go to the other whiteboard. So now we are going to talk about Kirchhoff current and voltage laws. These are very fundamental. I'm sure you've heard about them, but I'm just going to go over them and define them formally. So let's start with Kirchhoff's current law, or KCL for short. You will hear KCL a lot. Right? So what is KCL? So where does it come from? Let's think about a situation where you have a circuit, you have a node that's attached to several different elements. So let's say each one of these elements, and again, we know that this is algebraic notation, right? So we can say each one of them at any point in time is providing some current, some charge, dumping some charge into this node. Q1, let's say this is Q2 of t, Q3 of t, Q4 of t, and Q5 of t. In general, n. So these are the charges at any instant in time that's being injected into this node. So if this were not a circuit, if this was a general structure, could I say something about the sum of all these charges? Could I say that the sum of these charges is 0 for I equals 1 to n, whatever, where n is the number of these things? Could I say that in general? When it's not a circuit, when it's just like a general electromagnetic structure. There's no constraint or requirement about the relative frequencies and wavelengths and things of that sort. No, some of you are shaking your head. What can happen? Charge accumulation, right? You can actually get charge accumulating on this node, on this point. This is the conductor, right? You can have charge on a conductor. You've seen this probably in sort of physics. You can have a ball, and then you can charge it up, a metallic ball, and it would start absorbing things. that's just a standalone object, right? So that can, but within the circuit constraint, we saw last time that within the circuit constraints, there was something, when we assume, for example, the speed of light is infinity or something like that, then we saw that the conservation of charge reduced to this. Divergence of J is 0. And that means that there's no charge accumulation. Yes?
If there's no charge accumulation, how do capacitors?
Yeah, no net charge accumulation. Sorry, yeah, I should be more precise in talking. No net charge, so I should write that. No net charge accumulation. A capacitor accumulates exactly the same amount of positive charge on one side as it does on the other terminal, negative charge. There are some special cases where we need to deal with later on at some point that happens, but again, that's because this node has a capacitance. If this node is an ideal node, this will not happen, but this node can have a capacitance. If you make it out of a big metal that has a capacitance to ground, then you really have a fifth element here, or sixth element, which is that capacitor to ground. And if you take it into account, again, there's no charge accumulation. You just need to think about these things because there's a negative charge accumulating on the other side. So, but that's not what we are talking about right now. So now, but this is true for circuits. And we are in circuits domain, right? So now if this is true, it should be true also for the derivatives with respect to rates. This is a stronger statement than saying that its rates are add up to 0, right? Because I can say this, that I of t, nice notation, is equal to 0. Because this could have added up to some constant, right? And this wouldn't, because when you differentiate it. And this comes from the fact that I is dq dt. I'm just differentiating both sides. So this basically says that the sum of all the currents at any instant has to be 0 in circuit domain. And that's basically KCL. Does it make sense? Also keep in mind that when you have an element right? Within the circuit domain, this current and that current are instantaneously the same. So because of that, the current that comes out of this side is the same current that has gone through this side. And that's important when you look at the overall accounting of all the currents everywhere, at every point. Now, that's not necessarily true. I gave you an example last time, right, of something that is not true for, in general, that's an example of where this is not true when you don't have the circuit assumption. What was the example? Does anyone remember? An antenna, right? If you have some piece of wire, I can drive current through this end of it, and there's no current coming out of the other end. There's a current there's a charge distribution because that's actually comparable to the wavelength. Or transmission lines are also examples of these things. When things that are very long, you can have examples of these things. All right, any questions on this? Nope. So the other thing we are going to be talking about, the counterpart to this, is the KVL, or Kirchhoff's voltage law. With your permission, I will just write it KVL. Right? Now, what is KVL? So let's imagine that you have, again, we talked about meshes and loops and nodes and things of that sort last time. So you have a circuit where there are multiple elements or branches, essentially, that are connected in different ways. I'm just making some arbitrary thing here. And this is part of a bigger network. It doesn't have to be the entire thing by itself. We are showing just that we are looking at a segment of that. Right? So this is some arbitrary thing I drew. There's no significance to the or fundamentally important thing about this particular drawing. I probably wouldn't even be able to reproduce it. Okay, so now what does KVL say? KVL really comes from the Faraday law. If you think about Faraday law that we talked about last time, what did Faraday say? Faraday said curl of E plus dB dt is 0. Or in the integral form, which is not as compact, but probably easier to understand, at least initially till you get used to this kind of notation, is that it says the integral of E dot dl over a closed path. Right? So you have a path, you have a closed, let's say, loop in space, is equal to negative d dt of the integral, double integral, over the surface of B ds. The flux, the magnetic flux that travels through this, that the rate of change of that is equal to the integral of E dl around this closed loop. Right? So it says that if you have time varying magnetic field, so I have a little loop and I have magnetic field changing through this, it induces electric field. That is not conservative anymore. If you go around the loop, you will accumulate some energy. Right? Now, so then the assumption is that if you do not have time varying magnetic flux through this loop, either the loop is too small to pick up any magnetic flux, or your magnetic field does not change, then what you can say is that you can pick any loop. I'll pick one, let's say this loop, but you can pick other loops. It doesn't have to be a mesh. It can be any loop, any closed loop. And the sum of the voltages, so let's call this, I don't know, V1, V2, V3. We should keep the polarities consistent, obviously, right? V4, V5, V6. Thanks goodness it's over. So now it's basically sum of all these voltages, the algebraic sum of all these voltages, if there is no magnetic flux, which is the assumption that you make here, is that the sum of VI's for I equals 1 to m equals 0. No changing magnetic flux. So in other words, if you have a fixed constant magnetic field, it's not going to matter because of this derivative. If you have a small enough loop that doesn't pick up enough, it doesn't matter. Now, but in general, this is not true. I mean, you can have a situation when magnetic field is coupled into something, and that's taken into account as a special case with transformers. That's why we use transformers to capture that magnetic coupling, magnetic flux change. But KVL essentially is this sum, that for any loop, for any closed loop, you have the sum of all these voltages being 0. Now, let me ask you, so in this example, this sum, let's write this sum in this example. So this sum in this example is V1 plus V2 plus V3 plus V4 plus V5 plus V6, right? Now, but I defined these polarities to be this way. But you don't have that luxury all the time, right? So let's say I had defined other polarities here. So let's say V7 here is like this and V8 is like this. And let's say I pick a different loop. I pick this loop. How should I write KVL in that loop? So I can write V2 plus V3, for example. V2 plus V3. So if I start from here, so well, let's say I can go in this direction, say V3 plus V2. But then now here, I'm entering into the negative terminal. So what should I write? Minus V7 and then minus V8. It doesn't mean that I have to go and flip these things, because there's no way I can make it positive for everything anyway. So just keep it the way it is. I just keep track of the orientation with respect to that. And then if this happens to be pointing the other way, then V7 and V8 would be negative or positive. Does that make sense? Any questions? and KVL and KCL. KVL and KCL are essentially the constraints that come from physics, and they're abstracted away. There are certain assumptions behind both of them, right? And as long as those assumptions are satisfied, they create very simple set of rules that allow us to reduce the problems in this example, in the circuits, to simpler problems. Now, circuits is an interesting thing by themselves, and they're useful and all those things. But this should serve as more than just the circuits for you. And you will see as the class progresses, this is not limited to circuits. This is a way of attacking problems. You start with a physical problem that's very complex. You try to come up with reasonable assumptions that allow you to still deal with it. You reduce it to a mathematical abstraction. Circuits is a good example of that mindset. But it's not the only thing. So the purpose of this class is not just to teach you circuits. It's to teach you that way of thinking about reducing a mathematical problem. This could be a problem in the financial markets. This could be a problem in a chemical plant. It could be a problem in anything. There are lots of things that can be dealt with this way. But you have to understand the physics of it, and you have to have the right mathematical tool to be able to abstract it away and be able to keep track of the assumptions you're making along the way. All right. Any questions? Yes?
Besides antennas, is there any application where you use like a cheap magnetic flux to violate KVL for like some reason?
And you mean beside transformers?
Yes.
If you're talking about KVL. Oh yes, everything. I mean magnetic induction essentially, all of that. I mean you could argue that there's some sort of a transformer, but it's that, for these proximity chargers, you've probably seen them with some of the phones have them and all those things. Those are essentially magnetic induction charging. So you have this primary, essentially create a primary where you alternate the magnetic field and couple energy into the secondary that's picked up. So you do it through space, through the magnetic coupling without having an electrical contact. There are a large number of, all the power transmission network is based on transformers and magnetic coupling, because you do not distribute, I'm sure everyone here knows, you do not distribute the 110 or 120 volts. And there's a good reason for it, which we can discuss probably in a few minutes when we talk about the power of a resistor and all those things. So to distribute hundreds of thousands of volts, and then you bring it down to 480 and 240 and 120 and things of that sort that you use locally. Those are perfect examples of that. There are many, many, many examples. Anything essentially having to do with electromagnetics and radiation and radio and transmission involves even more than just magnetic induction. It's an electromagnetic coupling. It's even more. It uses both of those time-varying terms in the Maxwell equations. Otherwise, you won't have waves. You won't have propagation. The mere fact that you can see me really goes back to the fact that those two terms are coupled to each other. Otherwise, we wouldn't be seeing anything. Any other questions? All right. Okay, so that's for KVL and KCL. Now, let's go back to continue our discussion on that voltage source, the sources. We talked briefly about the sources, but let's talk about these ideal sources. So the question is, how do you model them? And what do you say about them? So we're talking about ideal sources. Again, we are still in the realm of definitions and the basics and the fundamentals to make sure everyone is on the same page, we have solid ground. So it's essential that everything that I say should make sense to you and you should be comfortable with it. If you're not, absolutely feel free to stop me as many times as you want. As many times as you want. I would be very happy to answer those questions. Okay? So ideal sources. Sorry. So let's start with the voltage source. We talked about a voltage source first, right? We have defined it. What is a voltage source? If you have an IV characteristic curve, it is just a mathematical function, really. It's nothing more than that. You're saying, if I draw a straight line here, I can say voltage, whatever that voltage is, let's call it V0, that's my stationary, stable, constant source. So this is essentially, like some of you said, is an ideal battery with a voltage V0. Now, in general, these things can be time varying. You can have a time-dependent source, and sometimes we show them like this. Basically, so this can be a V of t, where V of t is a function of time. Now, this is a different thing from this. this is still true, this shape, this flatness of this thing. So what happens in this case is that you have a function, you have something, the current becomes, or the voltage becomes functions of two things, the current and the time. But its functionality of current is a constancy. So for example, if you have a voltage source that's changing with time, what it means is that this line is moving up and down with time. It's a function of two parameters. But it doesn't mean that this line is going like this. It still means that the voltage would be fixed no matter what current you draw out of this thing for an ideal source. Okay? Now, that's the meaning of an ideal voltage source. The other thing, so let me ask you this question. What is a voltage source? A constant voltage source whose voltage is 0. So if V0 was 0, what is that? Think for a second. A wire, you say. Well, yes, a wire is a good way to answer it. Formally, if you wanted to find it, it's called as what? A short circuit. No, not a ground. A short circuit. Ground is something else. We'll get to ground. But it's a short circuit. Or wire. Wire is a good way to think about it. I think wire, I say short circuit. So, again, if you want to speak physically, you say wire. If you want to speak mathematically, you say short circuit. Definition of short circuit essentially is this line. A circuit whose voltage is 0 no matter what the current is, right? No matter how much current you pass through this thing, it basically shows you no voltage. It drops no voltage. It has 0 resistance. We'll talk about that in a second. So there's a counterpart to this, right? So this is a voltage source. What is the counterpart to this? Current source, right? Another one of these recurring themes that you will see in this class and a lot of things is the duality. There are duals to things. And particularly in this domain, there are a lot of dualities. And if you kind of think about them, you will see that some of the things are very similar. It's just basically two different representations. We'll see a lot of these duals. So current source. What is a current source? How do you represent a current source in that IV plot? Well, the VI plot, actually, in this case. It's a vertical line, right? So it's like that. And the symbol for it is something like this. There's another symbol for it that you may see from time to time. It's less commonly used, but it is used. It's like this. So that's also a current source, if you see. That's two interlocking circles. Yeah, you have to put some sort of marking on it. That's why this is preferred. Yes, you will see current sources of that nature too. I mean, drawn that way too. I mean, but this is probably the most prominent, so we'll never use that one. And that's the way we will be showing it. I don't know how visible it is from where you're sitting, but okay. So now the current source also. So let me ask you the same question I asked about the voltage source and see if you can use your powers of extrapolation in combination with duality. What is a current source whose current is 0? It's an open circuit. It's an unconnected thing, right? Because it doesn't pass any current no matter what voltage you apply to it. It's an open. Again, we are defining, these are mathematical ways of speaking about them. And the same thing about current source is true, is that basically it can be any value, it can change with time and all those things. So now, if I put voltage sources, let's talk about voltage sources. If I take voltage sources, let's say constant or time varying, it doesn't matter. Let's even make them general. If I take two voltage sources or n voltage sources, V1 and V2, and put them in series, what is this equivalent to? Think about KVL. It's the sum of the two voltages, right? Because basically it's this and that. Through any loop, you have to add these in series anyway, and they're constant. So this is equivalent to a single voltage source with a voltage of V1 plus V2. And similar thing for current sources. If I have two current sources of value I1 and I2 that are in parallel, now from KCL, you can see that this current is going to be the sum of these two currents, and this current is the sum of these two currents. So this is exactly equivalent to something that produces the sum of the two currents. And that comes from KCL in this node and that node. Right? Make sense? Good? All right. So these are good ones. These are fine. So let me ask you this question now. So you say, well, hey, you did series for these guys and parallel for that guy, for those guys. Why? There are two more combinations, right? You conveniently skipped over them. I said, yes, I did. I said, what happens if I take a voltage source? Let's make it a little bit simpler. You say, okay, sure. How about a voltage source in parallel with another voltage source? A 1 volt voltage source in parallel with 2 volt voltage source. 2. What is that equivalent to? What is it?
Locating the nearest fire extinguisher?
Yes. Probably a lot more than that. But yeah, that's a good way to think about it. It's the end of the universe. But now, what is it? Well, you can come back and say, wait a second, what do you mean? I can take a battery, 1 volt battery, and put it next to a 2 volt battery. I can still do this for the more physically minded of you. Yes?
Isn't it just a short circuit with voltage running through it?
What is that? Is that I don't know. You say it's a short circuit with the voltage running through it. I don't understand what that is. I'm intentionally being a little bit rigid in responding to you, because I wanted to differentiate between the mathematics and physics. Yes?
Really in parallel if you make the loop?
So one suggestion is that they are kind of really in, you mean in series? You mean they're in series because you are forming a loop. So is that true? Let's think about the definition of the series and parallel. Right? Parallel is basically when, you remember we formally defined parallel and series. That's why we formally define things, so there's no question about it. These are in parallel because they are sharing two nodes, right? I mean, they have also common nodes. So you could say they are in series, but they're series on both sides. But the question really is, what is it? What is there some, with this we were comfortable. You were comfortable. Nobody even frowned as far as I could see when I said, oh yeah, this is basically these two. Everyone was nodding, yeah.
Capacitor with charging through relational ones then?
Where did capacitors come from?
The one with 2 wires.
All of these things that you guys are saying could be true. And could also, and so would a million other things. But that's also an interesting way of thinking about it. Yeah. Yes? Which one will dominate which one? Why would the two? Okay, so that's an interesting hypothesis. The hypothesis here is that the larger one will dominate the smaller one. Why is that?
It generates a higher potential.
Sure, but it's really a question of how strong they are, right? Right. The potential is a relative parameter, right? But it's an interesting way of thinking about it. But okay, all right. So let's keep that in the back of our head. Julie, and I think then what was your name? Sorry. Max. Okay.
Are we assuming that each node is connected to other things? Or is it
No, I'm just saying that this by itself, if I were to use this as put it inside a box and provide this to you, and I say, well, hey, this is you didn't complain about this one, right? When I say, oh, okay, this was what I was doing. So, well, if I have a box, can you distinguish these two boxes from each other? And you couldn't. My question is, what is it equivalent to? Is there something that you can say about this? I'm throwing you a really bad curveball here. But you have to find the root of my problem. I'm giving you a false dichotomy, essentially. There are two more there, and then we'll get, yeah, go ahead. Sorry, what was your name again? Will, okay.
Well, I mean, the problem is that you have a short circuit on both the top and the bottom, and the one in the IV curve with both voltage sources trying to establish a different voltage across the short circuit. But the short circuit can't have a voltage across this. You have like the voltage sources are going to start competing.
Okay.
The 1 volt's going to sink a lot of current. The 2 volt's going to provide a lot of current.
Sure. Yeah, there's some sort of a problem.
Yeah.
You're observing a problem, right? Good observation. Hold that there. Just let's hear the other one, Daniel, right?
You have violation of conservation of energy and violation of KVL because your net voltage isn't zero. And so this kind of
So you're saying it's a violation. That's right. Yeah, it's something happened. We've done something bad, right? So you guys are kind of right. So let me present it to you 2 or 3 different ways. Let's start with Will's way. When you put 2 things next to each other, attach them like this, you're trying to find a solution that satisfies the conditions that each one of them tries to force. In other words, you're trying to solve 2 equations and 2 unknowns. Each one of them provides an equation between its current and voltage. One of these IV curves are an equation describing the relationship between a current and a voltage, right? When you put 2 things in parallel, you're forcing 2 equations to be simultaneously valid because they're sharing the same current and they're having the same voltage, right? So you are trying to find a solution for these 2 equations that graphically means trying to find the intercept point of these 2 lines, right? The way I think about it is that you're saying these 2 voltages are equal from a circuit standpoint, right? This is as valid and exactly in my mind the same thing as writing this. And I'm not exaggerating. This is exactly that. This is where you need to understand the difference between physics and mathematics. That's why I've emphasized the difference between physics and mathematics. We've created a mathematical abstraction that fails to capture some of the features that are important when you actually try to do this. In other words, if any battery has an internal resistance, and so there's basically some resistance. In practice, if you say, well, I can still do it. Yes, you can do it, but you can't do this. What you're doing is this. And that has no problem. I mean, you can solve what it is depending on what those resistances are, which basically goes back to your earlier comment about how strong they are and which one dominates which one and all those things, right? But in the absence of those things, my model is not capable of capturing the physics. Therefore, you can enforce random things. Can I write this in mathematics? I can. It's a false statement. Can I put these things, 2 ideal voltage sources in parallel? Yes, I can. It's an invalid statement. Now, let me ask you quickly before we move on, what is do all of that in the current domain? For current sources. 2 current sources of different values in series, right? 1 amp in series with 2 amps. This says the current of this branch is 1 amp. This says the current of this branch is 2 amps. And the KCL implies 1 equals 2. I should put question marks here in case somebody shows up later. All right? Does it make sense? So do not fall into this trap. Do not fall in the traps that are set by yourself when you define a mathematical abstraction. You have to know what the assumptions are. There are also these quick things I'm going to talk about. Again, this is more of a symbol and definition than anything profound or they're important, but not particularly profound. The dependent sources. You can have so independent sources we are showing with these circles, right? The voltage or current, etc., etc. There are also dependent sources, what we call a source whose voltage or current is a function of other voltages and currents in the circuit. So you can have a dependent voltage source, and we show them with these diamonds, essentially. So where the voltage is a function of some other voltages and currents in the circuit. Or it could be a dependent current source, shown like this, where the current is a function of some other parameter, some other voltages and currents in the circuit. So when you see one of those diamonds, it means that it's a dependent source. It means that it's not independently set. And you will see they're treated very differently, and they behave very differently. These dependent sources, there are 4 special cases: a voltage-dependent voltage source, voltage-dependent current source, current-dependent voltage source, current-dependent current source. And again, all of them are a special subset of all of the combinations you can have. But you will see they're useful in modeling things like transistors, things like that 3-terminal devices. All of those things can be modeled with something like that. Any questions? All right. Okay. So yeah, let's take a little break now, and then when we come back, we'll continue our discussion about the resistance.